And I believe last year what we were charging $20 a pop to get him to autograph your textbook. But now that he's been on the Colbert Report and there's a new edition, I think it should be 21 this year. What do you think? Buy the book. Yeah, in fact, buy the book. So you got some of the background. He has degrees in astronomy from Princeton and Caltech. And say he's been at SETI for quite a while, and before that spent some time in the Netherlands doing research. And so without further ado, I would like to pass this over to Dr. Seth Shostak.
This is a wonderful room, isn't it? You get this lovely cosine theta effect here on the edges. Okay, so they have me talking about something that I really don't know very much about, but that would have been true no matter what the subject matter. Normally I talk about SETI, but that's at the end of the course, and Frank is going to do that, right, Frank Drake? Yeah, well, he should be, and if not, I mean. But in any case, so I'm going to talk to you about the beginning of the universe, the Big Bang. I don't know how many of you were around for that or read about it in the papers, if any of you know what a paper is. But I'll just try and give you a couple of ideas about how the universe got started, and if there's still time, this runs to what, 5? If there's still time, I'm trying to leave questions so you can grill me like a cheese sandwich. If there's still time, I'll talk a little bit about the future of the universe, because in fact, in some sense, we know more about the future than we know about the past. And it is sort of interesting to know what's going to happen to the universe. All right, this all falls under the rubric of cosmology. Okay? And all societies have thought about cosmology, I dare say. I mean, I don't know from personal experience, but I'm sure that it's true. This was Mike Angel's idea here, the Sistine Chapel ceiling. Here is God, you know, who, by the way, doesn't he look like one of your relatives? Here he is, you know, giving Adam some sort of inside info there. Every society has some idea of how the universe began. I mean, there's some sort of legend, there's some sort of idea there. This is one that was rather well known because apparently there was a lecture in which Bertrand Russell was talking about modern views of how the universe began. And some woman stood up in the audience and said, well, that's all rubbish. Because in fact, we all know that the world is simply a flat plate sitting on the back of a turtle. So that's a cosmological theory. Now, one thing that's different about astronomy, the astronomy is a very old science, of course. They say it's the oldest of the sciences. But it's an observational science, or at least it has been up until recent times. You couldn't actually go anywhere. You had to just watch, you know, the light that came to Earth or some other phenomena that actually arrived here on the surface of the Earth. So it was all observational. And that meant it developed this tradition that if you had an idea, a theory, it was only of interest if you could prove it by looking up into the sky and seeing evidence for it. Okay? So, you know, this idea that the Earth is merely a flat plate or maybe a shell here, I don't know where the elephants came in, there's some other influence there. But in any case, that in fact it's all on the back of a turtle. This theory has an obvious observational implication, namely that if you go to the southern hemisphere and look up in the sky, you should see tortoise shell. Now, those of you who have been to the southern hemisphere may have noticed that there is no tortoise shell. But nonetheless, when Bertrand Russell, so you can throw out this theory, but Bertrand Russell was challenged by this woman who said that this was true. And so, of course, he asked, but madam, what is the turtle standing on? And she said, well, young man, it's turtles all the way down. Okay? So this has become I think Stephen Hawking writes about this in his book, the famous idea of cosmology. Okay, but again, you can throw this out, right? You can throw it out because it's very easy to show that we're not on the back of a turtle. This was sort of the Greek view of the cosmos, an early Greek view, and curiously enough, it was centered on Greece, okay? And when they found out it isn't centered on Greece, they've been trying to have revenge ever since on the rest of Europe. Okay, so that's great. Now, but then they had this other view. This was the view of Aristotle. Of course, this drawing doesn't go back to Aristotle, but this was sort of the Middle Ages version, that the Earth was in the center, that sort of fancy dealy there. That's the Earth, and you see, then you come to the moon, then Mercury, Venus, Mars, whatever. Oh no, the sun is next. So everything went around the Earth. Now this is kind of a gratifying theory because it makes you very important. And I know when I was your age, I thought that was true. I've subsequently learned it's not true. This was a lie foisted upon me by my mother. Okay, so but this was the reigning idea of the cosmos. Everything was Earth-centered. We were the fulcrum, the nexus, the center of it all, right? And this had a good run because this was considered to be true for more than 1,500 years. This was the received wisdom. But there were problems with it. And the real problems began to start when people began to try and predict the positions of planets, right? In order to do that with this kind of system, you could make it work, you know, that the planets were all on perfect circles, the sun was on a perfect circle, the moon was on a perfect circle, and, you know, you could sort of predict where they were going to be next week, next month, next year, but only by sort of jury-rigging a lot of the computations. I'll show you one of the problems with that. Only real progress was made in attacking this problem and getting to what turns out to be the truth was when somebody actually measured something. Hallmark of science. To measure something is to know something. Well, here you see Tycho Brahe, who had a silver nose, apparently the result of some sort of sword fight in which he had his nose chopped off. Rather an interesting character. He was set up with an observatory on one of the islands there near Copenhagen, and he built these big, you know, essentially protractors in the observatory, and he just measured the positions of the planets and the stars. You know, the position of the planets relative to the stars. But because he built these oversized instruments, he could do this very accurately. He didn't have any telescopes. He didn't have any optical aid. He just did this with his eyeball. Okay? But he compiled all these data. And here was part of the problem. Here you see the night sky, or maybe you don't see the night sky, but anyhow. And the planets move around the sky, you know, at different rates. All that was known. But they don't just sort of move constantly across the sky. They sometimes make a jog. Like, here's the path of Mars, okay? You see it's moving across the sky, and then suddenly it does this. Very strange. You can prove this to yourself if you had the patience to go out at night and actually watch Mars, or some of the other planets. I think this is Uranus here, I'm not sure, but you know, it would do the same thing. They do this sort of thing, and the question was, why are they doing that? Why are they making this sort of little detour here, right? That was a bit of a puzzle. And in order to accommodate this, the sort of the Aristotelian view of the solar system had to be modified with all these little epicycles and, you know, special kludges and fixes and so forth and so on. Copernicus comes along and he explains it by moving the center of the universe to the sun and having the planets move around the sun. Now, you know that's the case. And by the way, in case you wonder why that produces this, you can look at this little diagram and figure it out. For example, here's the orbit of the Earth, right? And here's the orbit of Mars. Now, Mars is not only a bigger orbit, but Mars actually moves slower than the Earth around the orbit. Okay, so here are intervals of, you know, the Earth's position, and those are intervals of Mars' position, and they're a little closer together because it doesn't move quite as fast. But if you're on the Earth looking at Mars, that's the part of the sky you see. And as you can see, as the Earth catches up with Mars and passes it, right, the position on the sky undergoes that little jog. See that? Okay, so, you know, by moving the center of everything to the sun, you solve this little problem that had been known for a long time. Right? And it also turned out eventually to be much simpler to predict the positions of the planets and moons and so forth. So, you know, Copernicus was a little afraid of this because the Catholic Church was not very happy with the idea that the Earth wasn't the center of everything. If the sun were the center of everything, then these other planets had the same sort of, if you will, philosophical weight as the Earth, right? And maybe Jupiter had inhabitants. As it turns out, probably Jupiter doesn't have inhabitants. But if it did, and they didn't know, right, then maybe they're as good as we are, right? So, you know, philosophically, it was a problem to move the center of the cosmos 93 million miles. That's not very far. I have that on my Honda. They moved it 93 million miles to the sun. Everybody gets upset. Okay, so this was the first big step in cosmology. Cosmology in the old days referred only to understanding the solar system. Right? Today, we've got bigger horizons, but there it goes. So this was Copernicus's idea. He was so afraid, by the way, of the reaction of the church to all this that he published on his deathbed. Right? That's when the book finally came out. He didn't get to read the reviews, I guess. I don't know. I don't recommend this. If it's publish or perish, in the case of Copernicus, I guess it was publish and perish. All right, anyhow. All right, so there's the sun, and, you know, this is the modern view of the solar system. By the way, these perfect circles also went away. They had to be perfect, right? Because the heavens must be perfect, just like the sun couldn't really have those spots. It must be something in your eyes. Or the moon couldn't have these imperfections. Okay, so there's Nick. Now, the really interesting cosmology, that what we're going to talk about for the rest of this soporific presentation, is what about beyond the solar system? Because now we know that the solar system is, you know, just one small dot in a very large cosmos. Okay? What was beyond it? This is sort of an early idea, and in particular, this dates to after Newton, because Newton worked out the physics of the solar system. We saw a little bit of that from the presentation here. And it all looked like this giant clockwork. Right? Physics was simpler 100 years ago or 150 years ago when it was all just Newtonian clockwork. Okay? And so the idea was that if only you could just get, you know, out there a little far enough, you could see this clockwork, you could understand how the whole cosmos worked. Well, there were a few things that were noticed rather early on that were actually interesting clues to how subtle the universe really is. To begin with, there's this simple observation that many of you may have made, namely that it's dark at night. Now, if I ask you, why is it dark at night? You know, your answer may be, well, I'm tempted to say things. I won't say things. You might say, okay, it's only because the sun's on the other side of the earth. That's why it's dark. But you know, that doesn't explain anything. Yeah, sure, there's no sunlight at night, but you're looking out into space, and it's dark. Space is dark, mostly dark. Okay. And you might say, well, why is that a problem? Of course space is dark. I mean, there are a couple of stars and all, but it's dark. It's mostly empty. Well, here's why you might not think it should be dark. Imagine, here you are on the Earth. This is a schematic diagram, not drawn to scale. All right, here you have a bunch of stars. Now, okay, suppose you're on this Earth and you're looking in the direction of this star, for example. You look in this direction of the star, and you know, there's a little dot there, and if you could imagine sort of blowing it up with a big enough telescope or something, you would see, you know, this bright disk of a star, and it would be as bright as a star. Okay, all right, fair enough. Now you look in this direction, you see that too. And any of these directions, you look at it in the direction of any star, and you know, it would be very bright in that very small area of the sky. But you could draw any line here. If the universe is infinite, right, if it goes on forever, you would be able to draw any line you like in any direction, and eventually it'll hit a star. Right? So, in fact, the whole sky should be lit up to be as bright as the surface of a star, if it's infinite. Okay? Should be. Which it's not. Okay? Now, I mean, this is sort of like looking at an infinite forest. Right? If you just go to a small forest like you have here in Palo Alto or something, you see a couple of tree trunks. But if that forest went on forever, you would see solid trunk. Right? You'd see bark everywhere. Okay? So it's the same deal. Now, this is called Olber's paradox, by the way, because this guy Olber sort of pointed it out. He probably wasn't the first one to point it out, but who cares? He gets the credit. And since he's dead, he doesn't care. Olber's paradox, the whole sky should be bright if it's infinite. Now, why isn't the whole sky bright? Anybody here still conscious? Like to say something? Can't hear you.
Because it's not infinite?
It isn't infinite. It might be, actually, it turns out the cosmos might be infinite, but in fact, the real problem is that the universe is not infinitely old. So the amount that you can see is not infinite. Right? The universe, you all know how old the universe is? Everybody know how old the universe is? 14 billion years. That's all you need for your next cocktail party. It's good enough. You don't need it to the nearest fraction of a second. So 14 billion years, right. And that means you can't see any trees, if you will, or stars. You can't see anything that's more than 14 billion light years away because the universe isn't old enough for the light from that thing to get to your eyeball yet. Okay, so right away, there's the answer to Olber's paradox. There are lots of other things, by the way. It turns out that the universe is filled with dust and things like that. They tend to block the light, things like that make things dark too. And it's also the fact that the universe is expanding. We'll get back to that. And when it expands, it turns out that the light gets shifted to lower wavelengths. So, bright stars get redder and redder and redder, that kind of thing. But mainly, this right away, just the fact that you go out at night and it's dark, which may be of some advantage to your love life, that fact tells you that the universe hasn't been here forever. And that's something that even Einstein didn't know, right? Not at the beginning, anyhow. Okay. Now, aside from that, there were efforts to actually sort of map the extent of the universe. Once it was realized that, well, maybe it doesn't go on forever. There was this guy, Bill Herschel. This is his driver's license photo. Bill Herschel he was a musician. He was German, but he moved to England. He took a job as the organist in Bath. But he discovered Uranus, or was it Neptune? I think it was Uranus. He discovers Uranus, and as a consequence of that, the King George made him, the astronomer royal, which was a good gig because, he had income for life. He could sit back, drink coffee or tea. I guess it was tea, and not do too much. But he did do things. He tried a very simple experiment too. This is really simple. These are simple things. He said, look, I'm going to figure out the whole shape of the cosmos, and the way I'm going to do that is I'm going to take a telescope, because he had a telescope. I'm going to take a telescope and I'm going to look at this part of the sky, and I'm going to mark off 1 square degree or something on that sky. I'm just going to count how many stars are in that 1 square degree. And I'll look at this part of the sky and I'll count out how many stars are in that square degree, and then over here and over here, and all, as much as I can see, right? And that would tell me you know, if there are a lot more stars in this direction than in that direction, that might tell you, well, you know, the universe goes on for a greater distance that way than it does over this way, right? Or maybe it's just more concentrated that way than this way. He hoped to sort of unravel the shape of all existence by just counting up stars. I mean, this is sort of like, you know, maybe mapping, I don't know, a city, mapping St. Louis by going, well, wherever you are in St. Louis, by just looking around and seeing how many buildings you can see in each direction. You know, if you're looking toward downtown, you'll see more buildings. If you're looking toward the suburbs, you'll see fewer buildings, that kind of thing. So he did this, and he came up with this picture, which, by the way, also looks like some sort of microbe, I'm sure. Okay, so this was William Herschel's map of the universe, but in those days, the universe was our galaxy. Our galaxy was the universe, which was a galaxy, which was the universe. So this is it, the whole thing. That's it. Okay. All that detail is probably wrong. In fact, I'm sure it's wrong. Why did he go astray? Well, I'll tell you in a moment. You notice there's a dot in the middle. That's where we are. Turned out it looked like we were in the middle of it all. Now, this was a couple of hundred years ago. The whole idea was tried again by this guy, J.C. Kapteyn, a Dutch astronomer. And he made a map that was a little more simplified. It was just a big flat plate. The galaxy, the whole universe, was one big flat plate, and we were, well, there's the center. We were over here. Right now, how can you tell whether you're in the center or not? Well, you know, if it's a big flat plate and it's kind of uniform, you'd expect if I look this way and I look that way, I should see more or less the same number of stars. But if I look this way and I see more stars than I do this way, then that means, you know, I'm not in the center, right? Right? So that was the idea. Now, why is it a flat plate? You can prove that to yourself, you know, every time you go out into the country where you can see the Milky Way. You can see the Milky Way, you see, you know, there's stars everywhere, but this band has a lot more stars. Milky Way, just a bunch of stars. That means you're sitting in sort of a big flat plate of stars, and when you look along the plane of the plate, you see a lot more stars than when you look perpendicular to the plate. Straightforward. Kapteyn put us very close to the center of the Milky Way galaxy. That's wrong. We're not near the center. In fact, this cross should probably be out here. How did he go wrong? Right? It wasn't all that gouda cheese. What it was that there's dust between the stars, and Kapteyn didn't know that. And the dust between the stars sort of blocks the view, particularly when you look over long distances. It's sort of like trying to do that experiment in St. Louis where you're trying to decide, am I in the center of St. Louis or not? All right. I'm in St. Louis. I want to know, am I downtown where the action is, such as it is in St. Louis, or am I somewhere near the edges? Okay. Well, you just count, you know, how many buildings this way and how many buildings that way. If you find more or less the same number of buildings in every direction, you can say, I'm right downtown. If you find more buildings this way than that way, you say, you know, I'm closer to the edge of the city. If you find almost no buildings that way and a lot that way, you can say, I'm probably near the edge. That was the idea. But if it's a foggy day, you only see a few buildings no matter what direction you look at, and it doesn't really tell you anything. And that was the problem that Kapteyn had. This wasn't so long ago. This is 1900. I was already middle-aged. Okay, so Kapteyn made this famous map of the universe, the Milky Way. Later research showed that we were near the edge of the galaxy. The big controversy then became, well, is our galaxy it? Is it the only galaxy in the universe? Are there other galaxies? Because we already knew that our galaxy was pretty big. By the 1920s, people had been able to measure the extent of our galaxy. It's about 100,000 light years across, plus or minus 1 or 2. And it has a few hundred billion stars. These are numbers that are useful next time you're writing up something for Match.com. Now, while this was all happening, there were other puzzles that were developing in astronomy, and they involved these so-called nebulae, which is just, of course, Latin for, you know, clouds. This is a photo. Astronomers usually, in the days of film, would use negative photos, okay, because you can see fainter stuff that way. So it's a negative photo. The sky's white, the stars are dark. And you see these sort of blotchy things. And there was a big debate in the very early 1920s about what are these blotchy things, okay? Now, we know today that these are just galaxies. These are very far away, but nobody knew then because, you know, I mean, you could say, all right, maybe it's another galaxy like the Milky Way, and it's just very far away, and we're looking through all this crud in between. This is all just local stuff, like looking through a screen door at your backyard, right? The screen's in the way, and that's what all these stars are. That's all very nearby stuff, but this is really far away. It's much, much farther than any of these stars. That's one possibility, and it turns out that's the correct one. But the other possibility that was taken very seriously by people who had tenure at reasonably decent schools was that this was just a blob of gas in our own galaxy, and maybe it was where planets were being made, or stars were being made, or who knows what. Maybe some Klingons blew themselves up. Nobody knew. You know, that could be just nearby, right? So how do you resolve this issue? There was a big debate, in fact, called the Shapley-Curtis debates in Washington, D.C. about this. I think it was 1924. But in any case, how do you answer the question of whether this is nearby or far away? Somehow, you've got to measure a distance to that baby. All right? You've got to figure out a distance to it. And that's very hard to do. In fact, one of the hardest things in astronomy has always been, how do you measure the distance to anything that's very far away? It's still a big problem. It's a perennial problem. I think I've had three, I have to be careful what I say here. Do I have to be careful with you? I've had 3 girlfriends, right, who earned a very modest living trying to measure distances to things, right? Broke up with them. I broke up with them all. So, or really the other way around. Never mind. Okay, so how do you measure the distance of this thing? Well, you know, when you talk about measuring distance in astronomy, the first thing you do is you just use Greek geometry, right? The stuff you learned in the 7th grade, just high school geometry. That's how you can measure the distances to stars, right? You can see where this star is on the sky, make a photo like this, and then wait 6 months so that the Earth is, you know, moved to the other side of its orbit, so it's gone 2 times 93 million miles, and make another photo, and this thing may move a little bit, right? Because you've changed your position relative to a nearby star with respect to the stars that are much farther away. Just, you know, make a isosceles triangle and do a very simple bit of geometry, and you can measure the distance. That's fine as long as something's nearby. But when it's farther away, none of that works. It's so far away you can't measure the angles, they're too small. So what you need to measure the distance to something really far away is what astronomers call a standard candle. Standard candle. You won't see them for sale in Target, but what is a standard candle? It's something that you know the brightness of. You know that it's intrinsically so bright. Let me give you an example of how that might work. You might imagine a 100-watt bulb. Not that they have them anymore, but a 100-watt bulb is a standard candle. Right? So we get a 100-watt bulb because they're all about the same brightness, all 100-watt bulbs. So you get a 100-watt bulb, call it a standard candle, even a standard light bulb. We put it over here, and I'll stand back here with a light meter. I still have a light meter. A light meter, and I'll measure how bright it is. And the needle goes like that, okay? Now, Lynn comes up, she takes that light bulb, she moves it twice as far from me. Obviously, the amount of light I measure here goes down. By how much?
It's quadratic, right?
Yeah, goes down a factor of 4. Those of you who are thinking a factor of 2, you know, probably won't be able to live with yourselves for the rest of the day, but it's a factor of 4. It goes as the square of the distance, okay? All right, very simple though. And if she moves it another factor of 2, it goes down another factor of 4. So the deal is, if we do an experiment here on campus at night, and somebody has a 100-watt bulb, right, and they're holding it up way down the field somewhere, and I go out and I measure it with my light meter, I can tell how far away that light bulb is just by measuring how bright it appears to be if I know that it's a 100-watt bulb, right? Straightforward, simple, right? Of course, I need to know that it's a 100-watt bulb. That's the trick. Because if it's a 20-watt bulb and somebody switched the bulb, or they put a 500-watt bulb, then I'll get the wrong answer. So you need this standard candle. You need something in the sky whose brightness you know. And, you know, people thought of, oh, maybe the biggest stars in the galaxy are all the same brightness. They had lots of ideas. They still have lots of ideas. But the real answer came a bit later. And I'll tell you how that came. Meanwhile, while people were worrying about this, there was a sort of a parallel line of effort to do something else with these smudges. It was another way of maybe determining how far away they were, and that was to measure the light coming from them, split it up with a prism, and look at the lines in the spectra of those smudges and see whether these things were moving toward us or away from us, something you could measure using what's called the Doppler effect. Now, you all know the Doppler effect? Raise your hand if you don't know the Doppler effect. Okay, well, at least you're brave. The Doppler effect just means that if anything that's emitting a wave, like even a sound wave, when it's moving toward you, that wave will be shorter wavelength. It'll be higher pitched. When it's moving away from you, it'll be lower pitched. All right, the canonical example, you're standing by the Caltrain tracks, along comes this train, you're going, ear, like that, right? Or you're standing by 101, not that that's a good idea. You stand by 101, and the cars, you know, they have a higher pitched whine when they come toward you, lower pitch when they move away from you. You never hear the cars go, ooh-wee. They never do that. Okay, it's always the other way around. That's the Doppler effect. And by seeing the difference in pitch, the difference in frequency, you can measure how fast they're going. You can do it with starlight. This is an instrument to do that. This is on a telescope back in about 1910, right? This was at the Lowell Observatory in Flagstaff, Arizona, where the director hired this guy, Vesto Slifer. And they said, look, we bought this new spectrograph, and I put it on that telescope, and I want you to go measure those smudges. See whether they're moving toward us or away from us, and how fast are they doing that. Here's Vesto. I think he lost his contact lens in this photo. It's unclear. So here's 1911. Now, this was actually, you know, today this would be very trivial. But it was very, very difficult in 1911. The equipment was very clumsy. He spent a lot of time. You know, he started this project when he was 17, and as you can see, here it is a couple of years later. It was obviously a difficult job. All right. Vesto Slifer, he was able to measure about a dozen of these smudges, and he found that most of them were actually moving away from us. The light was shifted down to lower frequencies, and a couple were shifted up a little bit. Now, had he capitalized on that fact, had he pushed that a little bit, we would have the Slifer Space Telescope instead of the Hubble. Because he really found, what he was measuring was the fact that galaxies are all moving away from us, almost all of them. The universe is expanding. The biggest discovery in science in the 20th century, and he's looking for his contact lens. Okay, now Slifer was not a very aggressive guy, but this guy was, Ed. Here's Ed. He couldn't decide when he was younger whether he wanted to be a professional wrestler or whether he wanted to be an astronomer. As it turned out, and unfortunately for the other astronomers, he decided to become an astronomer. Now, I don't really want to belittle Ed here, but he apparently wasn't a very nice guy. You know, he lived in England for about a year or two, and then forever after always spoke with a British accent. Everybody knew it was phony and that kind of stuff. You know, whatever. All right, so here's Ed. Now, he had those results from Slifer, and he actually had his own guy to do more work, this guy, whom you've never heard of, Milt Humason. Here's Milton. High school yearbook photo. Okay, Milt Humason was, you know, doing the same thing, measuring how, you know, what speed these blobs are moving toward us or away from us. This was becoming important because it was becoming obvious that these blobs were not very nearby. Some of them were moving away from us at speeds that, you know, you don't see on 280. These are speeds like, you know, hundreds of miles per second. Okay, and in fact, at the same time that this was going on, this woman solved the problem of the standard candles. Okay, here she is, Henrietta Leavitt, doing her email. Now, Henrietta was one of the many people hired at by Harvard, actually. Harvard began hiring women to do astronomy at the end of the 19th century. And they hired them not because they said, well, women can do this. That wasn't it. It was because only women will do this. It was that kind of thing. They had a whole bunch of really dog work projects that required, you know, looking at tens of thousands of spectra that their telescopes had made, or doing, you know, really boring stuff. And they tried to get the guys to do it. And of course, guys are not good at that. They're not good at so many things, actually. But they're certainly not good at that. I mean, you know, the history of the phone company. They originally had men as phone operators, right? But they were right away, they were beginning to fight with the customers, and they got bored and started fighting with one another. They brought in women, and they worked, you know, that kind of thing. Anyhow, so Harvard was doing this. They were bringing in these women. These were very clever women. They graduated from very good schools, but they had never been allowed to do this. They had never been allowed to go work in astronomy. There was a very strong bias. And to Harvard's credit, they actually hired these women in. And as I say, they didn't give them the most interesting jobs, but they had them doing these really boring projects, which turned out to be the most important research projects in astronomy for 100 years, right? They made all the big discoveries. This isn't so well known, but it is true. Okay, so here was a project of Henrietta's. She was sent to South Africa, where Harvard had an observatory. And because, as it turns out, the most interesting things in the sky are all in the southern hemisphere. Right? You don't know that, but that's because the southern hemisphere sort of faces toward the center of the Milky Way, and also there are better galaxies there. In fact, the usual statement among astronomers is that God put all the astronomy in the southern hemisphere and put all the astronomers in the northern hemisphere. Okay, fair enough. But Henrietta was sent to the southern hemisphere. She was making pictures of a small galaxy that isn't very far away. This is called the Large Magellanic Cloud, named after Magellan, because he saw them when he circumnavigated the Earth. Remember, he went around the bottom of South America, and he used these things sort of to navigate, as if he discovered it, as if the tens of millions of people who are living in the southern hemisphere for 14,000 years hadn't seen these things. But anyhow, so he got the name. Magellanic Clouds. But she was studying a particular kind of star. called a Cepheid variable. I know, sounds boring. But it's a kind of star that for one reason or another, it's, you know, it's unsettled, it's upset, it's depressed, whatever. It gets brighter and dimmer on a regular basis. You know, it gets brighter, dimmer, brighter, dimmer. Okay? And, you know, she was just studying these things because it was really boring. Who cared? Variable stars, all right, give it to Henrietta. Now, the advantage of studying them in a nearby galaxy like this is that they were all at the same distance, more or less. I mean, you know, this thing's big, but it's far away. So they're all at the same distance in the same way that all the buildings are at the same distance from the Stanford campus. Right? It's far enough away that, you know, for practical purposes, they're all at the same distance. So here's actually one of her plates, and you can see she found, you know, at least 25 of them, right? You see these are small things. And she had to make these pictures, you know, every night or even twice a night, and then compare how bright they looked on these plates and measure their brightness. Hard, arduous work, boring, but she did it. And she came up with this very interesting result. Okay, here's a graph. They say every time you show a graph, you lose 10% of the audience. I have 12 graphs. So. Okay. All right, now, what's plotted here is just how bright these stars are as a function of time. And the time is in days. You know, you don't need a stopwatch for this. You just measure them every night. And this is a fairly dim Cepheid variable. And you notice that it gets brighter, dimmer, brighter, dimmer, brighter, dimmer over the course of, well, I don't know, it goes through a cycle in maybe 10 days. Okay? Up there are much brighter ones. Those are brighter. And they really are intrinsically brighter because all these things are at the same distance. And you see they take their time to get, you know, they take weeks to get brighter and dimmer. If you think about it, it kind of makes sense because it turns out that those brighter stars are also bigger. And so, you know, for them to get bigger and brighter and dimmer, I mean, they're bigger, they're slower moving, right? Okay, so you might say, well, so what? I mean, who cares? The reason you care is this. If you find a Cepheid variable somewhere, she had some idea of how far away the Large Magellanic Cloud was, so she had some idea of how intrinsically bright these guys were. She could say, look, all you need to do is find these things and see how long it takes them to get brighter and dimmer. How fast are they doing that? And if they're doing it very quickly, they're dim. And if they're doing it very slowly, they're bright. So now I know, is it a 400-watt bulb or a 100-watt bulb or a 20-watt bulb? These were standard candles. And all you needed to know what wattage they were was a calendar and making some pictures every night. Right? The study of the Cepheid variables. These are still considered, these are still important in determining distances in astronomy. These were the standard candles, and Henrietta did it. Now, then this guy kind of took over. Here's Edwin again, Edwin Hubble. I know that looks like a pipe in his mouth, but it's actually an anatomical deformity. Anyhow, Edwin realized, hey, Leavitt has figured out how I can measure how far away these things are. Because by 1925, 26, Hubble had pretty much proven that they were far enough away that they weren't in our galaxy, they were separate galaxies. And he began studying them, for example, in a nearby galaxy like Andromeda. So here's one of his plates, Andromeda galaxy. You can see that tonight if you, well, the moon's out, you can't see it. Wait 2 weeks, and there's no moon. Go out, look straight up, you know, at some decent hour when you're just about to go to bed, what, at 4 or 5, whatever it is. Now, in the middle of the night, go out, you know, you don't even need binoculars really. You can see with your eye if you know where to look. You can see the Andromeda galaxy. It doesn't look as nifty as this, but here it is. Okay, see that? Cepheid, right there. You can barely see it, but he found a couple of these guys, and he used Henrietta's results, and he was able to measure how far away this galaxy was. He figured it was about 500,000 light years. That's wrong. Turns out to be 2 million light years, but 500,000 was good enough. That meant it was way outside our galaxy, right? So he had a number for how far away it was. And thanks to the work of Slipher and Humason, he also knew whether this thing was coming toward us or moving away from us, and how fast. So he had these 2 pieces of information for about a dozen of these babies. By the way, just to give you an idea, here's a modern photo of the Andromeda galaxy from Hubble. And that arrow points to a, there's a Cepheid variable right there. So you blow up that photo, you can see here's December 17th, 21st. You see it's changing in brightness. You see how hard this is, even with today's telescope. This is a hard thing to do. Okay, Hubble made this plot in which he plotted, he had what, 20 or 30 of these things, maybe not even that many, right, of these smudges, and he measured, on this axis, are they moving toward us or away from us? If they're below this 0 line, they're moving toward us. If they're above the 0 line, they're moving away from us. Okay, so you see most of them, I mean, with the exception of these guys, most of them were moving away from us. It was like we had bad breath, and all the galaxies were moving away from us, right? He plotted on this distance, or sorry, on this axis, how far away they were their distance, determined from these Cepheid variables. And so you see they sort of spread out in distance till you get to 2 million parsecs, which is, like 6 million light years, whatever. Okay, but the interesting thing here, he's misleadingly, he's drawn these straight lines, trying to imagine this plot without the straight lines and see if you would have dared to draw that straight line. But he did draw this straight line, and what it shows is that if something was farther away, it was moving away from us faster. That was the big discovery of Hubble. Okay, so you can imagine, well, that's kind of interesting. Not only is everything moving away from us, but stuff that's farther away is moving faster. Now, how do you understand that? Well, the simple way to understand it is imagine one of the students comes in a fit of pique, brings a hand grenade and pulls the pin. All right, so they pull the pin, thing goes off, and you look at it, a few milliseconds later, and you'll see pieces of shrapnel, and they're all moving away from you, not surprisingly, but you'll also notice that the ones that are moving fastest are the ones that are farthest from you. Of course, they're moving fastest. They've gotten away from, away from the center faster. Okay, so this was saying, the universe is kind of exploding. All right. Having said this, then it was an obvious next step to say, now wait a minute, if the universe is blowing apart, with these data, I can just sort of run this movie backwards in my head and figure out, well, how long ago was it that somebody pulled the pin? When did the universe begin? Okay, and that was, the biggest discovery of the 20th century in science, was that the universe was expanding and that it had a finite beginning. Okay, in fact, George Gamow was the guy who suggested in a paper that that's how the universe began. It began at some finite time ago, and it's been expanding ever since. Now, not everybody liked this idea, because that means that the universe hasn't always been here. And philosophically, you may have troubles with that. You mean to say there was a time when there was no universe? Or like my niece came up to me once, she said, well, Uncle Seth, she said, what was there before the Big Bang? If it happened 14 billion years ago, and that's the number, what was there before? Right, you might want to ask that. And of course, I would always say, well, look, Becca, the problem with that is the Big Bang created time. There was no time before. See, so your question doesn't make any sense. She walked away. She was not satisfied with this answer. I can tell you, most physicists are not satisfied with this answer either. Okay, and in fact, Fred Hoyle never liked this idea. He's a very famous British cosmologist. He's somewhat less famous now because he had the bad form to die. But he, in fact, was being interviewed by the BBC. I think it was 1949, and the interviewer was saying, so Professor Hoyle, what you're saying is that the universe actually had a finite beginning. There was some sort of explosive event that created the universe. And he said, yes. There are people who think that the entire cosmos began with some sort of Big Bang. He was trying to be sarcastic, right? But everybody liked this term so much. Be careful what you say on the BBC. They like the term so much that it's been called the Big Bang ever since, much to the chagrin of Fred Hoyle. Okay, so that's where it came from. Now, if this is true, and not everybody believed it true, Fred Hoyle didn't think it was true, and there have been other cosmologists and physicists too, for that matter, who think it isn't true, that maybe the universe still was always here, and yes, it's expanding, but as it expands, more stuff is being made to fill the gaps. See, so it's just, constantly making more stuff, which, sort of leaks out. When you take a lot of stuff and you squish it down, it gets hot. You know this if you have a bicycle pump, right? If you push down, the air gets hot. Okay, you compress it. So it gets hot, and in fact, at some point, you can run this scenario all the way back to 1 second after the Big Bang. The physics all still works. You know what the temperature, at some point the temperature is really high. That's 10 to the 12 degrees. That's 1 trillion degrees, right? You don't need a sweater. 1 trillion degrees. But you could run it further back. It's even hotter, right? Very, very hot. You can run this scenario back all the way to 10 to the minus 43 seconds. So that's a decimal point, 42 zeros, and a 1. That's a pretty short period of time. After the Big Bang, the physics still works. Earlier than that, the physics doesn't work, because now the whole universe is so small that we don't know the physics. Okay. Doesn't mean that it wasn't there, but we don't understand it anymore. But you might say, well, hey, we understand the physics of the universe from 10 to the minus 43 seconds up until, last Tuesday. And that sounds pretty good. Why are you worried about that first 10 to the minus 43 seconds? Well, of course you're worried about it. Because, the creation of the universe depends on what happened before that. Right? So people worry about it. But anyhow, in the early days, very early days, in the first tiny, tiny fraction of the whole cosmos, it was very small, smaller than an atom, smaller than an electron, and really hot. I mean, really hot. Okay, and if it was really hot, there would be all this radiation, light, if you like. Very short wavelengths, but all this light everywhere. It would just be light everywhere. It would be like being on the inside of a fluorescent tube up here. Just light. You couldn't see your hands in front of your face. In fact, for the first 300,000 years of the cosmos, the first 300,000 years of universal history, the entire universe was flooded with light everywhere. You couldn't see anything. Right? Electrons everywhere. They were all so hot they couldn't hook up with protons and neutrons and make atoms. It was just too hot for that. Then it cooled down. Suddenly, you formed atoms, and everything got dark. And suddenly, there was darkness. There was darkness. And then, a couple of million years after that, maybe 100 million years after that, the first stars begin to form. Galaxies form. Eventually, you get planets. On some of them, you get a little bit of biology. Eventually, you produce Stanford students. Okay, but in the beginning, it's really hot. So you have all this radiation everywhere, light everywhere. As the universe expands, the light's still there, just bouncing around, going everywhere. But it shifts to lower wavelength. Right? Here's a little stupid little animation showing how that happens. As the universe expands, imagine the universe is on the outside of this balloon, and those are the wavelengths of light or something. And they go from blue to red here in this animation because they're getting to the lower wavelength. Now, this guy, George Gamow, figured this would be interesting because if the universe really began with a Big Bang, the whole universe should be suffused with the leftover light from the Big Bang. Except that because the universe has expanded so far, that light isn't, bright, ordinary light that you see with your eyeballs. It's radio waves. Radio waves. He said there should be these radio waves everywhere left over from the Big Bang. In fact, he even predicted what the spectrum of the radio waves would be, and that's what it was. All right. Now, this little prediction, I should say, was made, I think, in the late 1940s. Nobody took it very seriously, except some guys at Princeton. There's some people in the physics department who said, it might be interesting to look for this radio hiss left over from the Big Bang. Right? Because if we could find it, that would end Fred Hoyle's blathering on about a steady state universe, because it would show that once the universe was very hot and very small. So they were building a device. It was just a little radio receiver. It worked in microwaves, but anyhow, it was a little microwave receiver. It had a little horn, microwave horn, and some amplifiers and so forth. And they were going to just aim it at the sky and see if they could measure any radio hiss coming from the sky. It wasn't these guys. It was guys in the physics department at Princeton. Now, as it turns out, this was back around the time of the invention of paper, as I say, when I was a student there. And it turned out that one of my advisor, a guy by the name of Dave Wilkinson, actually, he was involved in this experiment. Now, I was a sophomore, and we were doing a lab with one of my buddies. And we looked out the window, and we saw Dave down there in the parking lot with this device aiming it at the sky. And I said to my lab partner, Rudy, what do you think Dave's doing down there? And he looks down, and he said, I don't know, it looks like a receiver of some sort, but I don't know what he's doing. We didn't know what he was doing. And I said, well, let's take this lab experiment and roll it up to the window. It was a klystron. It was a transmitter, microwave transmitter. We were using it for some experiment or other. And we aimed it down into the parking lot. And then, I modulated the power supply for it. I just tapped out in Morse code, what hath God wrought, or something. I think that's what I got. Right? Just as a joke. 2 months later, the news breaks. They found the microwave background radiation. And I have to tell you, for 15 years, I thought, my God, we did it. But it turns out we hadn't done it because the Princeton guys were scooped by these guys. Arno Penzias and Bob Wilson, these guys. They're engineers working at Bell Labs and also in New Jersey. They were like 30 miles away from Princeton or whatever. And they had this big antenna here. They were doing experiments to try and, optimize transatlantic communication. This was for the phone company, right? Okay. And so they had this big thing they were measuring, they were trying to measure storms over the Atlantic and whatever. But they would point this thing at the sky and they would get this hiss, right? All the time. They got this hiss, this radio hiss. They knew it wasn't in the equipment. They didn't know what it was. At first they thought it was, coming from the airports around New York, but they aimed it the other way and that wasn't it. Then they figured it was due to leftover, leavings, if you will, from some pigeons that were nesting in the horn there. So they crawled in, they cleaned it out. They say it was not pleasant to do this. Okay, but the hiss didn't go away. I mean, the birds were probably unhappy, but the hiss stayed. And finally they decided, maybe it's really there. Maybe this is a real hiss. Maybe it really is radio static coming from the cosmos. So they called up Princeton. It was the nearest university when anybody knew about this. And they talked to the guys there. And Robert Dickey, who was the professor who was working on this project, he went to the team that had been trying to measure this, and he said, boys, And they were all boys. He said, boys, we've been scooped. These guys won the Nobel Prize. Guys at Princeton got to teach another class. Okay, but finding this background radiation, this was the point they measured there. It fell right on the curve. And there have been all these other measurements since. Even Princeton got a few measurements since that show it's true. It's true. It's just leftover black body radiation, as it's called, leftover glow from the Big Bang. Penzias and Wilson, here it is. Okay, and this put to bed all these other theories. Surely the universe began with a Big Bang. Now, measuring this background glow is a project that's been going on a long time. These are not very interesting slides. They're not even my slides. But various spacecraft have been built to measure the background glow. Not so much to prove that it's there, because we know it's there. That was easy to show. But to see if there are any sort of, if it's modeled at all. I mean, it's a little stronger coming from that direction than from that direction. You would think that this is leftover glow from the very earliest days of the universe. The universe surely had some irregularities. Right? I mean, it eventually made galaxies. It couldn't have been just perfectly uniform. That even violates the uncertainty principle. It had to be a little bit irregular. And consequently, there ought to be these irregularities in the background glow. And you couldn't find it from the ground. I mean, none of the instruments from the ground were good enough to find these irregularities. They were very, very small. They're, a few parts in 10,000 or actually a few parts in 10 million. It's very, very small. But various satellites, including COBE and eventually WMAP, have mapped that background glow. WMAP, the interesting thing here is the W was named after this advisor of mine, Dave Wilkinson. I guess maybe he got something out of it eventually. So here's the background glow. This is just a sort of a map of the sky. And, yellow means it's a little stronger radiation. Blue means it's a little weaker. Right? But these are very, very slight differences. But there's a lot of information in these things. A lot of information. If you're a cosmologist, you study these things with an enormous attention because these things, in principle, tell you a lot about the history of the cosmos because you're looking at a baby photo of the cosmos. That's what these are. In fact, there's this first map, when it came out, a guy over at UC Berkeley, you probably heard of UC Berkeley, a guy over at UC Berkeley, George Smoot, who was involved in the project, he said, it's the fingerprint of God, right? And everybody said, all right, whatever. Okay, so there you go. See, that shows you the improvement from the first thing to map these irregularities, and this is the improved instrumentation. But here's one thing that you might be able to use it for. This was published by some guys in the UK, a guy by the name of Penrose and some other people, theoreticians at Cambridge. They think they see rings in this background glow. Now, mind you, these rings have been enhanced to make it easy for you to see the rings. When it's not enhanced, not everybody can see these rings. But you know what they're saying these rings are? They're saying, the entire cosmos might have been bumped into by another cosmos very early on. Right? The whole cosmos may be just something involving string theory membranes and things like that. And some other membrane may have hit us, causing the Big Bang and producing these blemishes, like dents on your car. Right? That's their claim. Maybe their buddies believe them. Not everybody's convinced by this. Okay, so here's the history of the universe. Big Bang, boing, and then eventually us. This is an important point. Thanks to astronomy, classical astronomy, we know how to measure the ages of stars fairly well. Right? And there was a problem in the early days when people thought, when Hubble had originally worked out the Big Bang. When you ran the movie back in the days of Hubble, or even in the 1930s and 1940s, the universe wasn't 14 billion years old. It only seemed to be like 5 or 8 billion years old. That was a problem because we already knew that some stars, very old stars, globular cluster stars, things like that, we knew they were more than 10 billion years old. You can't have stars that are 10 billion years old if the whole universe is only 5 billion years old. But, those were all just errors in measurement that are of no interest to you. As it turns out, the oldest stars are now, they're 10 billion, 11 billion, 12 billion years old. There's nothing in the universe that's older than the universe, it turns out. You can sleep better at night. That was an important point. Okay, there was another problem that came up. This is the last idea I'm going to give you about cosmology because this is becoming more and more important. The homogeneity of the universe. Homogeneity. In other words, it's about the same everywhere. This is a picture made by the Hubble Space Telescope, which should have been, of course, the Slipher Space Telescope. Here's a Hubble Space Telescope. This is what's one of these deep field photos. All right, so what they did is they aimed this telescope at some random piece of sky. It wasn't even random. They picked a piece of sky that was deliberately uninteresting. And they just looked at it for 100 hours. This is a bit of sky that you cover up with a pinhead held at arm's length. It isn't very much. You see a bunch of galaxies, all these galaxies, right? Okay. And even these little dots are galaxies. They're just farther away. There are 100 billion galaxies that you could photograph if you did this all across the sky. All right, but the interesting thing is if you swing that telescope 180 degrees and make another photo, it looks pretty much like this photo. Everywhere, the universe looks the same. And you might say, yeah, well, so. Well, here's the well, so. How does that galaxy know to look like the galaxies on the other side of the universe? Right? It's like you show up at a party and everybody's dressed in, I don't know, a barrel with shoulder straps or whatever, right? I mean, how do they know what the dress code for that party was unless there's been some communication along the way that somebody called up and said, you know, everybody's to dress like Lady Gaga or something, right? So the fact that the universe looks the same means that it's been thermalized. Something's happened. It's communicated. For example, if we put a big roaring fire over in the corner here, eventually the whole room will get warm, right? But it won't get warm faster than the atoms bouncing around from that fire have time to bounce on other atoms and communicate that heat to the atoms all the way over there. You have to have communication. It takes time. So for this galaxy to look like a galaxy on the other side, something has to have, some information has to have been conveyed from where that galaxy is to the other side. And you can say, well, okay, it did, so what? I mean, you know, all right, the universe. But this galaxy might be 10 billion light years in this direction, and you look at the other direction, you'll see another galaxy that's 10 billion light years in that direction. So they're separated by 20 billion light years, and the universe is only 14 billion years old. So they haven't had enough time to communicate. This galaxy doesn't know about that galaxy. It can't have gotten a phone call about the dress code, right? And you say, well, wait. Let's go back 7 billion years. We'll go about half the age of the galaxy. So now this galaxy is only 7 billion light years away, and that one's only 7 billion light years away. But wait a minute, now the distance is only 14 billion light years, and now the universe is only 7 billion years old, so they still haven't had time to communicate. There's a real problem. No matter how you work this backwards, they haven't had time to learn about one another's existence and to come to some agreement about, you know, what the properties are going to be, what the temperature is going to be. All right, a student by the name of Alan Guth was sitting in his car, apparently somewhere in Cambridge, Massachusetts, you know, like 20 years ago, whatever it was. And I don't know, he was thinking about this. It's not what I think of when I'm living in my car, but anyhow, that's what he was thinking about this. And he suddenly realized, wait a minute, I know how to beat this rap. I know the solution to this problem. That the universe hasn't always been expanding at the same rate. That at the beginning expanded really much faster. So there was a time when the whole universe was so tiny that there was enough time for a photon to get from one side of it to the other, to communicate, to make that phone call and say, look, everybody, this is the agreement, what we're going to be like. Okay? And he wrote in a little notebook in his car, big idea. He called it inflation. Right? And it was a big idea. I mean, Alan Guth has tenure at MIT, and, you know, he's written books. He walks down the streets of Cambridge, people recognize him, carry him on their shoulders, whatever. Okay. So that's the idea. Inflation was that, in fact, at the very beginning of the Big Bang, 10 to the minus 35 seconds after the Big Bang, you know, it's barely any time, right? Suddenly it goes, psh, it expands really quickly. Right? It expands from the size of, you know, smaller than an electron to the size of the solar system in that amount of time, 10 to the minus 32 seconds. It's much faster than the speed of light, of course, enormously faster than the speed of light. And you say, wait, can you do that? Yes, space can do that. Objects can't. Right? You can't move faster than the speed of light. But space can expand at any speed. That doesn't violate Einstein. Okay, so you have this idea. Here's a graph showing this. Right? Here's the time after the Big Bang, 10 to the minus 40. So, you know, we have physics. It goes back to here. But at 10 to the minus 36 seconds, suddenly the universe expands enormously. You look at how many orders of magnitude it gets bigger. And now, then it stops the expansion. All right, going on a diet, that's it. And now just, you know, continues to expand at the leisurely pace that it does today. So by having this inflation, he could have the universe at the beginning so small that it could communicate across itself and homogenize itself a little bit, make sure that the universe looked the same everywhere. Here's just another picture of that, same thing. We're out at 5, is that it? Okay. I think I'm going to stop here because I want to make sure that you have time for some questions. I could go into the future a little bit. Here's the... The universe is very, by the way, let me show you this picture. I said it's uniform, but it's not all that uniform. Right? If you look locally, this is fairly locally. Each one of these dots is a galaxy. Right? And you can see it's filamentary. There are big voids here between the galaxies. It's kind of like a web of some sort. That says something about how it was put together. This is actually a model. But our galaxy would be just one dot here on this web. It's just more of the universe. The universe is enormously large. You don't sometimes realize how big it is, right? Because here's a dot. That's a galaxy. And somewhere in there's a star that has a planetary system. And one of those planets is called Earth, and you're in there. But this is the rest of it. Okay? It's not even the rest of it. It's just some of it. I don't know if this animation even works. It doesn't, so never mind. Let me just give you the big ideas about the future of the universe. There are only a couple of things that we think could happen. To begin with, the universe is expanding, and it might just keep on expanding, but then again, all the galaxies are pulling on one another. There's gravity. So maybe this expansion will eventually come to a stop, reverse direction, and the galaxies will all come back together, and we'll have, sort of a Big Bang in reverse, known technically as the Big Crunch. Okay. This might happen. That's this graph. The universe gets bigger, bigger, bigger. Here we are over here, there we are today. But at some point it'll come to a stop, and then it'll start getting smaller. This will be great for astronomers for a while, because the pictures will get better and better of the galaxies as they get closer and closer. Of course, when you get to this big crunch, everything in the universe gets crushed into something that's really, really tiny, and that's going to, interfere with your gusto-grabbing lifestyle. Some people think that it would bounce, right, and you get another universe like that. But of course, all the information from this universe would get lost in the crunch, so all the rock and roll goes away, and you have to start over again. But that's one possibility for the universe. Another possibility is that, nope, it never, yes, it's slowing down, but it never reverses direction. It just keeps going forever. It just depends on how much stuff is out there. If there isn't very much stuff out there, then it'll just keep expanding forever. And every night you go out, there'll be less to see. Another possibility is that it expands forever, yes, but eventually, well, never mind that. That's not even interesting. It's either open or it's closed, like that. And I'm going to finish with this, because I had a few slides to show this, but the big discovery of the last 10 years in astronomy anyhow, and maybe in some sense you could say in all of science, was this. These curves are all wrong. People are trying to measure how fast is the universe, to what degree is the universe slowing down? Right? Is the expansion slowing down by this amount or that amount? Let's measure it, and we'll know, are we going to have a big crunch, or is it just going to keep expanding forever? And it turned out, nobody expected this. It turns out that the universe is not only not going to have a big crunch, but the expansion is increasing in speed. It's as if somebody has put their foot on the accelerator. The galaxies are not only moving apart, the shrapnel is not only moving apart, but it's picking up speed. Right? And this means that over the course of 10, 20, 50 billion years, you won't be able to see any of these distant galaxies. If there's anybody alive, if there's intelligent life anywhere, 50 billion years from now, they're going to have a real hard time with astronomy, because they won't be able to see most of the universe. It's gotten so big. So let me just finish with this. Here's the history of the universe in a way. You remember those little exercises you did in maybe grammar school, whatever, elementary school, where you'd have the history of life on Earth. Right? And you put pieces of paper around the room. Do they do that anymore? Right? So here are the first celled microorganisms, whatever, and then, stupid life, whatever. And then, eventually, after like 3.5 billion years of that, or whatever, you'll finally get multicellular life, which is a little more interesting, and things you can see under a microscope that wiggle around and have some sort of structure. And then eventually, you get trilobites and dinosaurs. And I say that I tend to belittle her field of study by calling it stupid life, but stupid life is a lot more prevalent than intelligent life, and that's something you can prove to yourself by walking around campus. So it goes around, and after 3.5 billion years, you get multicellular life, and then eventually you get, trilobites, and you get dinosaurs, and then the last, fraction of a centimeter right in here. Here's Homo sapiens at the end. Okay, that's the history of life in the universe. You could extend that backward a little bit and have the first, 500 million years of the Earth where there was no life. Okay, and that's it. That's the history of the universe so far, at least our part of it. But you can imagine extending this thing around. All right, well, Homo sapiens, but then there'll be thinking machines, there'll be whatever there are. We'll meet the Klingons, and we'll join the Galactic Federation, so on and so on. But eventually, after 100 billion years, the last star dies. Going to happen. Stars are all going to go out. Enjoy them now, right? Your gusto-grabbing lifestyle is doomed, at least if it depends on starlight, which it probably does, right? It goes out, but the universe is still there. It's still there. All that stuff is still there. It's just that, you know, the sun is now a charcoal briquette, right? And then all the other stars turn into charcoal briquettes. They're big, but they're charcoal briquettes. But the universe keeps going. It keeps expanding, keeps creating more space. It's more stuff. I mean, or not more stuff, but it's moving away, right? It just keeps going, keep adding those pieces of paper. And in fact, it never stops. You just keep adding pieces of paper forever. Now, the last thing to happen, and physicists can predict what's going to happen. All right, well, the stars have all died, but now we have some neutron stars and they do this. And then maybe after 10 to the 32 years, protons decay and so all matter becomes kind of misty. And so you can figure out all this stuff till you get to 10 to the 100th years. After 10 to the 100th years, by the way, that's a long time, 10 to the 100 years. Right? That's 1 followed by 100 zeros, years. You know, if you were sitting in a middle seat eating peanuts, that'd be a long flight. 10 to the 100 years, the last thing that we know about will happen. The last big black hole will evaporate finally. That'll be it. Nothing else will happen, right? There won't be enough energy anywhere at any place that you could get together to roast a marshmallow anywhere in the universe, but the universe keeps expanding. All this stuff is there, but nothing's happening. But it doesn't stop. So there you go. The whole history of the cosmos. Bing, 14 billion years ago, there's a big flash, right? And then after 100 billion years, you see you had galaxies, stars, planets, biology, intelligence, Stanford students, and then you get nothing. Not just for a long time, you get nothing forever. So the history of the cosmos was big, brief flash in which something happens, and then an infinity of nothingness. And you got to ask yourself, who designed this? Okay, maybe you have some questions. Yeah?
Do scientists have proof that no new stars can form? Because I thought some suns are older than others, and so if all of them keep dying, no new ones will ever be created.
Yeah, stars are being made now. I mean, you go out tonight, you look at Orion, you all know where Orion is, and you can look at the nebula in Orion that's in the sword, right? And you see it's sort of reddish. Look with a pair of binoculars. Stars being born there. Stars are still being born. There's still enough stuff, which is to say hydrogen and gas, between the stars to make new stars. But the trouble is, and when stars die, some of them, the big ones, they explode and blow their guts all over the place, which can be used to make new stars. A lot of the stuff in your body is, in fact, stuff that was blown out of some star quite a while ago, right? Okay, I mean, you know, you may not want to, it's not a romantic thought, but it's true. All right, so, but the trouble is that most of the material is getting locked up in stars. Some of them explode, but they only blow some of the material out. So you're using more material than you're giving back, right? So you can work it out, and people have. At what point do you not have enough material to make any new stars? And it's on the order of 100 billion years. Make it 1 trillion if you're picky. That'll be it. You won't be around.
So I was thinking about something. So you're talking about how all matter is pulled apart and everything is body. So this includes. So I'm not sure if this includes or not. Just a question before I ask my question. Is this? Do the particles themselves get ripped apart?
Yeah, you mean because of the expansion of the universe? Yeah, the acceleration of the universe might, in fact, lead to a scenario that the guy at Dartmouth calls the Big Rip. Not the Big Rip-Off, but the Big Rip. Because if that's really true, if there's something blowing the universe apart, and there is, they call it dark energy. Nobody knows what dark energy. What is dark energy? I went to a hydroponics shop in Mountain View. They had dark energy in a bottle. It cost $15, but it was for growing marijuana. I didn't know. Yeah. Little did I know. But yeah, so they call it dark energy, and it's blowing things apart. It depends on the properties of dark energy. One possible property of dark energy may be that it's getting stronger with time, that this acceleration is itself accelerating, that they're, you know, like that. In which case, you can work out how long will it be before, you know, the galaxy begins to blow apart. There's something here about the Big Rip. The Big Rip. This is what happens at the end of the Big Rip, right? 1 billion years before you get to the end of the Big Rip, all the galaxies will, you won't see the galaxies. 60 million years before the final scenario in the Big Rip, Milky Way begins to fly apart. Months before the end, planets in our solar system will start to wing away from the sun. Earth explodes 30 minutes before the end. At the very end, you know, atoms begin to blow apart. This is going to interfere with whatever you have planned for that day because every atom in your body will blow apart. The Big Rip. This is one way to end the universe, and you don't have to get all that paper for it to go around forever. Okay? It doesn't look like this is likely to be the truth, but it could be the Big Rip.
I guess the reason why I'm asking is if you consider so protons and neutrons themselves getting ripped apart, they're made of quarks.
Yeah.
And I heard that somebody a few years ago proved that you can't have quarks without partners, that you can't actually isolate them. So I'm just a little skeptical about all this because if everything's getting pulled apart, these quarks would get pulled apart too, but you can't find them without partners.
Yeah. No, it's true. You can't have free quarks, it doesn't seem, Yeah, well, maybe you get some quarks for a while, but then, they get ripped apart.
I mean, would they get ripped apart as well?
Well, I think so, but honestly, I don't know about the Big Rip's implication for quarks. And if quarks are big in your life, and in some sense they are, or they're small in your life, I guess. Yeah, I don't know the answer to that question, whether the quarks... I think that everything gets ripped apart, though. I think it's all... Yeah, I mean, in some sense, like I say, it's unfortunate. You would love to think that the quarks at least survive. I don't know why, but yeah.
Just wondering if there's any room for optimism of, they're using dark matter to explain the problems they're having with predicting galaxies and things. They're kind of supposing dark matter without observing it yet. And so I'm wondering if there's any room for optimism that maybe they just have gravity wrong. And, who knows, maybe we do get a big crunch and we get an oscillator. Is there any possibility of that in the scientific community, or am I just...
Yeah, I think you mean dark energy in this case, not dark matter. Dark matter could be wrong, too. It could be the gravity is not correctly described by Newton, 1 over r squared kind of stuff. In fact, my best buddy, who's still working in Holland, he spent the last, I think, 15 years working on that, which is unfortunate because it's probably wrong. But anyhow, it's his choice. I don't say anything. But that's dark matter. Dark energy is what you're referring to. Could it be that indeed the universe won't keep expanding forever, that maybe there's just something wrong? I don't think it's very likely. I mean, the first place you always look is something wrong with the measurements, with the calibrations, with the standard candles, because they do that using a kind of standard candle that's known as a type 2 supernova. They're not using Cepheid variables as standard candles for that thing because the galaxies are so far away. When you're trying to measure the expansion of the universe, you can't use those Cepheid variables. You have to use something bigger and brighter. So they use exploding stars, supernovae. And there could be something wrong with the calibration of those things, and maybe it's all just wrong. Mind you, Saul Perlmutter across the bay here, who just won the Nobel Prize 2 months ago for finding some of the big evidence for dark energy, would be very unhappy to learn that he won the Nobel Prize because of a measurement error. All right? So, and I think that he would tell you, as would the other astronomers who've been doing this for a while, because they've been doing it now for a while, 15 years or something. And it's unlikely that it's a measurement error at this point. This is not like, the neutrinos going faster than the speed of light. That could very easily be a measurement error. Probably it is. But the acceleration of the universe looks like it's for real. Doesn't tell you what it is. Nobody knows. There are various possibilities. You might have your own theory. Nobody knows what it is. But the fact that it's accelerating seems to be pretty solid now. Wouldn't rule out, altogether the possibility that it's not. But it seems pretty solid. Does that disappoint you? Yes?
So you were talking about how the homogeneity of the universe was a problem that led to the formulation of the expansion theory. But I was wondering...
Inflation.
Inflation theory,
Yeah.
right. You said basically that galaxies that look similar across the universe had to communicate with each other. But I was wondering why that would necessarily be the case if the entire universe was just governed by the same set of physical rules. We do not expect similar galaxies to form on it.
Well, what's governing the formation of galaxies? You have this initial universe. It's very small. It's very hot. You got gas. If the density of the gas over at this part of the universe was a heck of a lot different than the density over at this part, then you would make fewer galaxies over here than over there. So something has ensured that the conditions over here, yes, the physics is the same everywhere, but that the conditions are pretty much the same over here as over there, because you see the same density of galaxies. They not only look the same, but the number of them is more or less the same, the density and so forth. So the whole universe it's like a room that's all at the same temperature. It must have had enough time for the heat from the the radiator over there to get to all the atoms in the room. There had to be a time when they could communicate in the sense of thermalizing it, making sure it's all the same temperature and the same density.
Also, are you, when you're looking that far back, are you really looking at different sides of the universe, or are you actually looking at, in some senses, one single point, which is the Big Bang, no matter which direction you look?
Well, if you look far enough back, when you're looking at the cosmic background here, the fingerprint of God, you're looking at, indeed, that very small part of the, yeah, you're looking back toward the Big Bang. You're seeing it everywhere, but that's the Big Bang. Yes, ma'am?
My questions are pretty much exactly the same as his.
Well, really? Do you know him? I mean, how is it this is the same? Yeah.
I won't. So I heard this theory the other day that, there was this theorem, right, that in a closed system, closed dynamic system, there's a 100% chance, given infinite time, that a state will reoccur. And so the idea is that if you're in heat death, then any instance in time could potentially just spontaneously be created. Like this could be in heat death right now. Did you have anything to say about that?
Well, I'm not quite sure what the point is, but here's the deal. We talked a little bit, we did talk actually about what might cause the Big Bang. There's reason to think, this is fairly sophisticated theoretical physics that I don't work in that field either, but it suggests that Big Bangs are just a natural thing that happen in some sort of meta-universe. There's a problem actually with the fact that our universe is so conducive to you being here. Right? As Freeman Dyson said, it's as if the universe were expecting us. Right? Because if you change some of the physics constants a little bit, you can make sure that stars don't work. And if stars didn't work, you wouldn't be here. Right? There are a lot of, a handful at least, of constants that if you change them by 10 or 20%, the universe would not be conducive to biology and you wouldn't be here. So the question is, how is it that our universe is indeed so nicely tuned for our existence? And one way you can answer that, again, you can just appeal to theology, or you can say, look, if it weren't true, we wouldn't be talking about it. Well, that's true, but I don't know if you buy into that. Okay, the anthropic principle, it's called. But here's another solution that's very fashionable these days, and that is to say that our universe is just one of many. Right? There are Big Bangs going off all the time and always have been, and they're making universes all the time. There are universes all around, and except for those rings there that were the suggestion of another universe. We don't have any evidence of these guys, right? But there are universes everywhere. So sort of like, you throw some bubble bath into your tub, turn on the water, you get all these bubbles, and all of them are universes. And, the next universe over might have 17 dimensions instead of whatever number of dimensions we have. And, there's no life in there, but it's like having zillions of lottery tickets, because the number of universes, there's the number I saw, 10 to the 128. Who knows where they got that number? But, that's a big number, okay? And most of these universes are worthless. But, of course, you're going to be in one of the good ones, right? It's like, hey, I won the lottery. The chances that you win the lottery are pretty small, but if you're a lottery winner, you can say, look, all those other lottery tickets, and mine is the winner. Of course, because you're the winner, you're noticing it, right? So this solves the problem without requiring anything very special about us, that there are just lots and lots and lots of universes, most of which you couldn't get rid of on eBay, but ours is good. And here we are talking about it. Okay, so this is, as I say, this is a fashionable theory now. Whether it's true or not, we don't know, because it's hard to prove the existence of other universes. Multiverse, parallel universe, you've heard these terms, and that's one of the strong reasons for suspecting that it's true. The other strong reason is, insofar as we understand how you make Big Bangs, it could be that you could make a Big Bang right here in this classroom if you just knew enough physics, just twist time and space the right way, and bam, you create your own universe. Okay? That would look good on your resume. You might not be able to get into it, right, because it's got its own dimensions, it's over, but so that making a universe, our universe might be the science fair project of a high school kid in another universe. I mean, who knows? But it may be that universes are very easy to make, and that's why there's so many of them.
Very quickly, in addition to the speed of light question that's been confirmed, sort of, might be wrong measurements, there's people that are measuring in New South Wales distant galaxies and found fine structure constant seems to vary slightly.
Yeah.
Yet the physical laws vary. It would be more interesting than other universes that you can't measure. It might be that a lot of the universes couldn't have us, but in this section.
Yeah, they're trying to address the question of, really, is it true that the physics is the same everywhere in our universe? Or could there be Big Bang? Could there be Big Bangs going off even in our universe, other places? Could the laws of physics change? And there is indeed this Australian result, I think, in which they seem to have found that one of the physical constants, the fine structure constant, is indeed different in other parts of the universe. But call it.
If you spread that out in space, this stuff is minor in the local areas. When you spread it all the way out to distant galaxies, that this redshift matters.
Yeah. Well, as far as we know, the laws of physics seem to be the same. You can look at the spectral lines in these very distant galaxies, and they tell you something about how atoms behave in that galaxy, even though it's billions of light years away. You understand something about how atoms behave in that galaxy. And with the exception of this kind of result, which is, I would say, tentative, it seems to be the same everywhere. Okay, I'm kind of running over time.
Physics majors in the room?
Yeah, too many.
You'll be amused to know that during Seth's lecture, I got an email from the physics department. Apparently, they've got a colloquium speaker next Tuesday named Seth Shostak. And all of you are invited, although the physics department feels that this may be way above our heads.
No, it's not at all. It's not going to be above your head. This is about SETI. It's not about this stuff.
So,
I wouldn't dare speak about this stuff.
We'll send out a coursework announcement. But I think we should certainly give Seth a big hand.